Welcome to the Explainer. Today, we're unpacking a fascinating and honestly, absolutely crucial subject: how massive, complex, and safety-critical systems are actually proven safe before they ever see a single day of real-world use. Listen, when you're engineering systems where human lives are literally on the line, we're talking massive transportation networks, intricate signaling grids, automated control centers, crossing your fingers and just hoping for the best? Yeah, that is definitely not an engineering strategy. So today we're looking at the meticulous, uncompromising path to operational readiness.
Okay, let's dive into this. Here's our roadmap for today. Number 1, the purpose of testing. Number 2, verification and validation. And number 3, the testing regime. Let's get started.
Section 1. The purpose of testing, or as I like to think of it, the independent safety net. Think about the wildly high stakes of deploying these complex systems. Massive investments, intricate hardware, millions of lines of code, and all of it has to work flawlessly in some incredibly harsh, unpredictable environments. Like I said, crossing your fingers isn't an option. Testing is our ultimate safety net. It's formally defined as an independent process used to assure fitness for purpose before operational service. Now, independent is key here. It means you absolutely cannot grade your own homework when safety is involved. And fitness for purpose? Well, that means it is unconditionally ready to handle the exact real-world job it was designed to do, long before it ever goes live. Moving on to Section 2, verification and validation, the twin pillars. So in casual conversation, people use verify and validate completely interchangeably. But in engineering, distinguishing between these two concepts is the absolute crux of ensuring safety and reliability. They are fundamentally different things. First up is verification. The key question here is, are we building the system right? Notice the emphasis on how it's built. This step is all about the blueprints. It's the process of demonstrating that the specific, documented requirements of every single individual development phase are perfectly fulfilled. It's kind of like baking, actually. Verification is proving you followed the recipe exactly, gram for gram. If the recipe says bake at 350 degrees for 30 minutes, verification proves that is exactly what happened. It is strict, literal compliance with the design. But contrast that with our second golden question, validation. Are we building the right system? See, you could perfectly verify a system against its blueprint, but what if the blueprint itself was totally flawed for the actual environment? To stick with our baking analogy, you followed the cake recipe perfectly, it's a beautiful cake, but the customer actually ordered a steak. Whoops. Validation zooms out. It confirms that the entire finished system actually solves the real-world problem the end user has. So the crucial point here is the contrast between the two. Verification means you fulfilled the blueprint perfectly. Validation means the blueprint actually fulfills the real-world need, and you absolutely must have both. Think about it. A perfectly verified system that doesn't actually solve the problem is completely useless. But on the flip side, a validated system that wasn't rigorously verified during its build, that is fundamentally unsafe because you just can't guarantee how it was put together under the hood. And this brilliantly illustrates exactly how these two pillars work in practice. This is the famous V model of systems engineering. If you trace the path down the left side, you're moving from high-level concepts all the way down into detailed design and manufacturing. But look at the path coming back up on the right. As you build the system back up, integrating parts, testing them out, you're constantly checking back across the V. Those lower levels, that's your verification, checking your build directly against the design specs. But right up there at the very top right, that final overarching check all the way across to the initial concept. That, my friends, is your system validation. All right, Section 3, the testing regime, proving the system. We've looked at the high-level philosophy of the V model. Now, let's get into the highly practical, chronological testing gauntlet that every single system has to survive before it's certified for use. We've got 4 critical steps: unit testing, qualification testing, integration testing, and interface testing. You'll notice a really logical progression here. We start at the absolute micro level, dealing with isolated code, then we move into the physical world with hardware, then we combine them, and finally, we test how they communicate. Let's break these down. The journey begins at the micro level with unit testing. This is carried out by the software developers, and it focuses on totally isolated blocks of digital code. Before this code is allowed to touch a single piece of real hardware or interact with anything else in the system, it has to prove it completely complies with its specific requirements. And the depth of this testing? Well, it often depends on what we call the safety integrity level, or SIL. Basically, the more safety critical that piece of code is to human life, the more punishing and rigorous this unit testing is going to be to ensure there are zero hidden faults. Now, while the software is being tested digitally, the hardware goes through qualification testing out in the physical world. Operational environments are brutal. A piece of equipment might sit in a freezing tunnel, bake in the scorching summer sun, or just be constantly rattled by the massive vibration of passing trains. Hardware developers literally push their equipment to the absolute limits here. They subject it to extreme shock, intense vibration, sub-zero temperatures, saturating humidity, the whole shebang. Because if a component is going to fail, we want it to fail right there in the laboratory, not out in the real world. Let's move on and see how this all builds together with integration testing. So we've got bulletproof software. We've got hardware that could survive a hurricane. Next, we literally plug them into each other. We combine those subassemblies and subsystems, and we need to confirm that when the software sends a command, the mechanical hardware actually responds exactly the way it's supposed to. We are hunting for any unexpected, emergent behavior that only pops up when you finally put these incredibly complex pieces together. Finally, we reach the last hurdle, interface testing. This check is absolutely critical because, get this, you can have two perfectly integrated, totally flawless subsystems that will still cause a total system failure if they can't talk to each other. We're checking the physical cables, the wireless data links, the network protocols. If the physical and digital connections between those pieces of equipment aren't communicating flawlessly, the entire system is compromised. Imagine a perfectly functioning sensor trying to send a critical stop signal, but it's going through the wrong type of cable. No way. That is exactly what interface testing prevents. So we've covered this meticulous journey, right? From the core definition of testing, through the twin pillars of verification and validation, all the way down to that grueling practical testing regime. So I want to leave you with this thought. What are the real-world safety implications if a massive, complex system actually goes live without this rigorous, independent testing regime? It's a pretty sobering question. Because at the end of the day, this exhaustive, multi-layered process is literally the only thing standing between a theoretical blueprint on a desk and dependable, life-saving safety out in the real world. Keep that in mind the next time you rely on some massive piece of complex infrastructure. Thanks for joining me for this explainer.